Good afternoon, treasured colleagues. I'm Toby K. Today, I'm going to give you my best nuts and bolts understanding of mutability, also known as record versus class in V4 Gamma. Just a disclaimer, I'm not an official V4 core developer. I'm also not here representing any company I work for. I'm just sharing my very limited general knowledge as an individual developer. For anybody who has come here from YouTube and doesn't know what they're looking at, this is the V4 Gamma editor. It's a real-time visual coding environment for .NET. I'm a big fan. We use it in the car industry for prototyping quickly because it's fast to develop, fast to iterate, but also well supported. We can connect it to a lot of things. There's lots of Nugets all the time, great community. It's free for non-commercial use. You can download it right now at visualprogramming.net. This is an intermediate tutorial for V4 Gamma. It's going to be a long video so that I can deep dive into the real nuts and bolts of the examples. I hope this can be reference material if you're running into these problems in your existing projects. And at the start and end, I'll also try and give a higher level view that might be useful when you think about the architecture layer of your next project. This will truly be an extended tutorial split into 7 parts. I'll try and talk slowly and clearly, which makes the video longer, but you can always increase the playback speed if you prefer. My last comment before I start is that my original motivation for making these patches was increasing my own knowledge because it's a topic I've been rough on in the past and still sometimes now. First, you want to get the latest V4 stable, then you want to go to Manage Nugets and, whoa, slow down. Okay. I want to ask, you funny? You think it's funny? My wife thinks it's funny. Okay, that means it was a great joke. I want to ask you, Patcher, to be security conscious. I know lots of you are pros, you're already across this, but I've put up Nugets, they let me do it. It's not hard to do, and somebody could easily put malicious code up there. And I support Nugets. I want everybody to put up their code and share it. I think that's great. We all want to embrace an open world and say, come on over, anyone can learn to code, download these examples, but please be careful and think about where these instructions are coming from. If you come from the official v4.org or v4 chat or a GitHub, you can tell that's all legit, that's great. For example, in this case, you should be able to tell this video is uploaded by TobyKLight, same author on the Nuget and related GitHub if you want to check out those links before you download the Nuget. Sadly, bad guys are out there. We haven't had a major security issue in the V4 community, but I don't want there to be. So please think about where your code comes from. Okay, but once you're sure I'm legit, you want to click up here in this top left menu, which is very small on this 4K monitor. You get Manage Nuget's command line, and if you type on the command line Nuget install VL.ExtendedTutorials, it's going to install these patches, and you can follow this along in the help browser. You'll be able to, let me bring up the help browser. In the help browser, go learn extended tutorials. And yeah, here we are, 01. We're running the patch right now that we're talking about. Okay, let's talk about mutants. What is mutability? It's a programming concept. You probably already heard it. Mutable objects can change. Immutable objects cannot change. But that doesn't make much sense because, of course, the strength of objects is changing them. Just some read-only objects doesn't sound very useful, so what does this practically mean? A practical simplification would be to say that when a mutable object is updated, the same blocks of memory are changed. Updating an immutable object means under the hood a new copy of the object is created. I'm simplifying this to make it about the memory footprint. Really, mutability is an abstraction at the language level, and more things than this go on in memory. But for me personally, thinking about mutability in the memory context makes it more concrete. It's always better to show rather than tell, so I've made a visualization. Again, this is a simplification. Memory doesn't really look like this. It's just something to illustrate the concept. We have an immutable record on the left and a mutable class on the right. In C#, I think records can be mutable, but in VL, it's simplified and records are always immutable. We can tell which is which at a glance in the UI because on the left, the immutable side, the links are solid, representing flow of data. On the right, the dashed lines represent references being passed. I'll explain that more in a moment. Both the class and the record we have here are just 4 bytes. You can also see that in the memory representation we have here, and they both have an operation that only increments byte C. Let's run that increment operation on the class first. If I right click here, you can see byte C is going up there in our memory visualization, and it's mutating the same block of memory. Now let's try that increment operation on the immutable record. This time, it's making a new copy of the entire record each time. So that's actually a pretty simple concept. Updating mutable objects mutates the same memory, and a mutable object cannot mutate, so changing that involves making a new copy of the object. They get the same result in the end, so you might be thinking, what's the big deal? Let's have a look at another example to answer that. This time, we will fork our data flow and create 2 paths for record and class. Let's go through the left immutable side first. At the top, a record is created. Then we fork it here into 2 pads. They both run the increment operation and save again, assigning to their own pad to create a loop. Let's increment these and see what happens. As you might expect, when we increment record 1, it makes new copies of record 1. When we increment record 2, it makes new copies of record 2. We fork the path, and now we have 2 independent records. What you see is what you get, which is great. Now, let's go through the mutable side on the right. Our class is created, then these dotted lines represent that the class is a reference. We fork it to 2 separate pads. Let's run the operation. Run it on class 1, and now let's run it on class 2. You'll see both of them actually increment the same instance. Why is that? We only created one class up here, then we assigned it to 2 pads. Even though these have different names, we actually assigned the same instance, or the reference to the same instance, into both of these pads. So when either of them is increased, we're operating on the same instance. On the left side, with the solid links, this represents data flow. If I fork it, then I'm going to have 2 separate objects to operate on. On the right, that's not necessarily true. I can send a reference to multiple places and still be working on the same instance. This is the high-level difference between mutable and immutable. When we see a solid line, we can be confident that the application in this patch is a description of operations on data. If I trace the solid line back, I will get a very clear picture of what has happened to this data and why. If I could only see part of this code, I could still be confident what was happening to the data. On the class side, I could have copied that same instance reference all sorts of places all over my application. In a complex use case, I can lose track of why this class is mutating. On a nuts and bolts level, this difference has a lot of implications about how you code, and that's what we'll go into in the next parts. One detail from my visualization is you might think the records are making a big trail in memory that could be some kind of problem. So it's not usually a problem. In most use cases, that memory is made available more than fast enough for other objects to use. There is one important case in V4 where immutability is considered to impact performance, and we will cover that at part 6 of this video, Spread versus SpreadBuilder. Okay, that was part 1. Now let's start going through the details of what mutability means in practice for record versus class. First difference we will look at. Records must be explicitly stored to update them. On the left, we are creating a record. On the right, we are creating a class. As before, they both consist of 4 bytes. They both have an identical operation to increment byte C. At the bottom, we're reading out both of these, and we can see the value of byte C. The difference here is only that for the record, we must have a pad at the bottom to store it in. If I delete the link and press update, you'll see nothing's happening down here at the result. If I restore that link and press update, it works. On the class side, I don't need to save it in a pad. I can just increment it as is. This makes sense. To this increment operation, I can't mutate the existing record. it has to make a new copy. In fact, at the bottom of this if block, or at the bottom of the operation, it's already made a new copy and it has to know what to do with it. On the class side, we don't need a pad at the bottom. Why doesn't the class need a pad to write back into? Because the class is mutable, an operation that runs on a class will modify, mutate, the reference that is passed as input. This means the reference contains both the data the operation needs for input and the location where it should put the result. It doesn't even need the border control points in the if region. As long as the reference reaches the operation, it can operate on that reference to mutate it. This is the difference we were talking about in this whole part 2. In v4, you generally have to store or assign or do something with your immutable types in order for them to be useful. Mutable types, theoretically, only need their input reference to achieve input and output. Okay, so what are the consequences of this difference that records must be explicitly stored? The first consequence we already touched on. Let me just get rid of those. The first consequence we already touched on, and it's something you hear a lot in discussions of mutability, and that is immutable records are meant to be easier to reason about, which is meant to lead to better code and less bugs. Let's compare this. On the left side, we have a record that is split into two paths like we did before. On one side, we have increment byte A. On the other side, we have increment byte C. Only byte A is being saved back into this record 1 pad. At the bottom, record 1 is being split and only byte A is incrementing. Byte C increments, but you see the value only stays at 1. It's never saved. It can never increment on that value. That makes sense, I would say. If you look at that, you'll understand what's going on, why byte A is incrementing and byte C isn't. On the right side, we have the class. The class is being sent to two operations, the same, increment byte A, increment byte C, and then both are counting up, which is also great. And you can see in such a simple program, it's also fairly easy to understand what's going on. This is the classic argument that the left is a really clear description of the result, and the right, if increment byte A and increment byte C were split in different parts of your program, maybe you're going to lose track of what's going on. That being said, I think there's many times that the class on the right is actually very useful for exactly these properties, and it might be the right choice in the right context. This becomes a bit more complicated in the next example. Where people say you really have to use an immutable object is when you have async tasks, or else it's going to be very difficult to reason about your code, and you might get into very serious issues like race condition. So let's do it. Here we have another example similar to what we've done before, except this time the increments are happening automatically. So you can see these LFOs, and they're happening in async tasks. Again, record on the left and class on the right. If we jump down to the outputs here, you can see we are getting different results. Why is that? Let's look at the right side first. The class is passed into the async task and it runs the increment operation. The class is also passed to the output pin here, but actually that's irrelevant. Like before, the operation just has to run. It only needs the input. It only needs that output because the async task region won't run unless it knows the type of the output pin. The timing of these tasks is intentionally such that every second trigger, because one is 2 seconds and one is 1 second, every second trigger they're going to happen at the same time. And when we look at the output here, you see sometimes it goes up by 1 and sometimes both go off and it goes up by 2. Let's instead look at the left immutable side. We have the same setup basically, except we are using the outputs. Then we're bringing those outputs in, and when we receive them, we then have this code to merge the results back into a record. What's happening here that's different and why we have a different result is because the code here is giving precedence to the rightmost path. If they both trigger, then only this lower path's result is going to get passed in, meaning that the value only ever goes up by 1. Now, before I drink the immutable Kool-Aid and tell you how amazing the solution on the left is, I think anybody would look at this and say, well, the example on the left is more verbose, looks harder to read. On the right, the class is incremented twice, the value goes up twice. That's not rocket science. Why is this immutable side meant to be better code? Essentially because we are forced to write a solution to this merge problem. If you have a bunch of async tasks that do happen to do the same thing, then yes, you probably should have some code that solves what happens if both tasks return together. Of course, if you know from the start that you want the performance of async, then maybe you would avoid an architecture where you have this identical operations and need to solve this merge problem at all. The next consequence of records needing to be explicitly saved is to do with stateful processes that happen inside an object. At this point, I should mention some people would say an immutable record is not an ideal place for a stateful process to be running. I would say you certainly can do it, so you should know about this detail. So here in this operation that happens on the record, animate byte C, it's running an LFO, which is a stateful patch. It's a process, you can see by these two gray lines here. And inside this particular process, it does have a stateful functionality. That's counting up when it runs. You can see we split the record and it's counting up. The difference between mutable and immutable in this case is that we must save the record into a pad for this state inside this process to run. The process itself needs somewhere to save its state that's embedded in the record. And if I delete this link, you'll see it's no longer able to increment. Over on the class side, as before, it only needs the class reference passed to the input to be able to run any internal processes. It can use that same reference as before for taking the input data it needs and having somewhere to put the results. Let's look at the next consequence of having to explicitly store records. What I'm about to show you is not considered best practice object-oriented programming. In fact, I'm sure a lot of what I've shown you is not. And you can see it's not very elegant, so I think I would agree. The case here is we have a hierarchical object, and that's in an object in an object. In this case, we have arm record. Inside arm record is hand record, and inside hand record is finger record. We want to just update the finger. We're doing the same on the left and right. The difference, because we need to store the record, is that if we want to store the arm record again, we need to rebuild this object. And that's what all this code down here is about. On the right side, if it's done with mutable classes, I only have to go through the parent objects to access the child object. Once I have that child, I can update it without requiring any further repack of the existing tree. I can also put that reference somewhere else in parallel. So I could also have a dictionary that contains all the objects in the tree in a flat list, look them up by some key system, GUID. At the same time, they also exist in the tree when it's useful to access them by tree. And whether I access that reference via the dictionary or via the tree, I can update the same object, which can be a very useful property of working with references. There is a workaround to improve your life if you ever end up in the situation on the left. There's a node called try replace descendant that will do some of the repacking for you under some conditions. The notes with this is you can only update an object that already exists. If you created a new slice in the spread here, you would have to rebuild. Try replace descendant won't be able to cope with that case, and it only works on a single object. You can't put a spread into try replace descendant, although you could make a sort of fake object that just consists of a spread in order to get around that. Okay, we're still looking at the difference between record and class, focusing on the difference that records must be explicitly stored. This example is similar to the others we've seen where there's a fork in the path and we do some parallel operations on our object. Then for the record, we have to have a process to manually merge those properties back if the result we're looking for is, of course, a single object. What's unique about this example is that the four operations are now doing different things. You can see they're increasing byte A, B, C, D. Unlike before, we don't have competition with two async tasks trying to increment the same property. I think this is a pretty common setup that you might have an object with different processes around your application, have clear responsibilities to only update particular properties. I only really bring this example up to say both sides, whether you use record or class, can be improved by verticality. Here we get the same result. The code is cleaner and easier to understand. Even if you don't have a preference of what processes happen first in your application, for example, you don't care if the agents run their movement or their collision detection first, it can still be worth imposing an order on that and passing the objects through vertically just to make your code easier to read and easier to reason about. On the class side, it also forces an order of operations, which we'll talk more about later. There's one more workaround. If you want to use an immutable record, which is great, but you also would love to have the flexibility of a reference that you can pass around the patch, you can explicitly turn an immutable record into a reference with the reference nodes. You can create a reference, which you should do when you create the record, and then you'll be able to retrieve that same record and be able to set it anywhere in your patch. This also brings back some of the drawbacks of the reference, like order of operations might become unclear, but it can be a good hybrid approach to solve certain problems. For the last part of this section on how records need to be explicitly stored, I want to show you a pattern you might run into if you import a Nuget that's not already set up for a V4. In V4, we're used to our nice data flow objects with inputs at the top and outputs at the bottom. Do you remember before I said with a mutable class, you only need to provide the reference, and that reference can be used to both provide input and write the output? Well, that pattern is used fairly often in C#, where a mutable object or variable is provided as an input that is intended to be mutated by the process in order to provide your result. It would go something like this. The documentation for this library for cooking says you have to create a stove and a fry pan. The stove has the cook operation and it takes a fry pan full of ingredients. But the cook operation doesn't return anything. In the class documentation, it's got a declaration starting with void, meaning it has no output, or maybe just bool, meaning it only returns if it was successful. Either way, it doesn't seem to have an output of food. So how are we meant to get anything out of this stove? In this case, the cook operation mutates the contents of the fry pan we provide as input. And if I hit that now, on my completely fake operation I've created as an example here, now the fry pan is cooked, we read the outputs of the fried pan, and we have fried steak. To guarantee order of operations, so we don't try and read the fry pan contents before it's cooked, use an if region like this. Even though the fry pan instance isn't connected as an output, it still guarantees the order of operations that cook is executed before fry pan split is executed, because it will calculate everything inside the if region before anything connected to the output of a border control point. More on this later. Okay, here we are at part 3 of this huge deep dive on mutability in V4 Gamma. We are looking at the differences between working with immutable records versus mutable classes. In this part, we focus on change detection. Change detection is useful because it's often a great way to only call expensive processing when we need it. So how does change detection work? To quote the Grey Book, the changed node should probably be called changed reference, as it is only capable of detecting exactly those changes where it gets confronted with new objects. So, because records create a new copy when they are updated, this effectively means anytime a record updates, a change is detected. So, difference. On records, changes in data can be detected. On class, change only detects when a new class instance is assigned or created. Let's look at this in practice with our first example. We have to keep our eyes down here on the changed node. When this bangs, a change is detected. In the first box, on both sides, we increment byte A every frame. On the left side, change is detected every frame. This makes sense, we're changing it every frame. On the right side with the class, change is not detected because the class is not being reassigned, only mutating. In the second box, we enable the set byte operation. On the left side, change isn't detected until we actually change the byte, which is great. It means it's only reacting on the data of the record being changed. On the right side, nothing happens in any case. The changed node still doesn't see the class mutating. In the third box, we only read data. On both sides, this correctly is not registered as a change. In the fourth box, we explicitly create a new record object. It has the same data as the old object, so although nothing is changing because we're explicitly creating a new object, this is registered as a change. With the class, this is the only thing that the change node will pick up as a change. Let's look at how this applies to the cache region, which detects change the same way. This is a fairly common application of cache where we have the drawing processes for stride or skier cached. They should only update when the incoming object is changed. The cache regions have a has changed output, so you can tell when their contents are being executed. And wait, both of these are triggering even though nothing is changing. What's going on here? You probably already noticed we're creating a new object every frame on both sides. So this is a bad example. Let's try again. Okay, this is the same as above, except the create nodes are properly on the create operation. Now, the cache regions are not registering change every frame. We have some further operations here to set their properties that are not on the create. On the immutable record side, we change the color, and you can see the change is triggering and the output is changing. We can also change the spike count. That's great. On the mutable class side, the cache region does not see those changes that only mutate the class. We have to use the force pin in order for those changes to pass through to the output. Let's look at a couple of workarounds for detecting changes in classes. The first is behavior subject. This is a powerful but quite complicated reactive programming paradigm. Basically, the behavior subject is a reference that notifies subscribers when it has an update for them. In this case, we prepare and send this update when we detect our primitives changing, not the class changing. Then the update notifies the drawing cache region about this new information. This pattern will be much more powerful when you have other parts of your application reactive as well. The second workaround is much simpler, and I've implemented this a few times. I highly recommend it. Basically, you include a primitive value as one of the properties in your class that is specifically for downstream change detection. Any operation that should result in a downstream draw call simply increments this value. Let's look inside the class, and you can see when we set the byte, the ticket property is incremented by 1. Back out here, you can see it detects when the ticket property is changed. However, it's not true change detection. It doesn't know if my input here has actually changed. All it's seeing is that I'm running the set byte operation. Theoretically, you could also implement different kinds of tickets that could call different kinds of downstream processing. Another nice bonus is that it tells you, because you're incrementing a value, how many times you've tried to call your downstream process. We've made it to part 4 of this deep dive on mutability in V4 Gamma. Here is another difference between working with immutable records versus mutable class objects. Because updating a record creates a new copy, it's possible to take snapshots of these copies. This functionality is needed for nodes like sample and hold. Let's look at that in detail. We have on both sides a value that is being animated. On the left immutable side, we hit the bangs to take some snapshots of that value. As expected, we get the snapshot at the time we hit the bang. On the right side, we use the same method, but you'll see what we get in the result is the live value. All that happens is we're taking a snapshot of the reference, and the reference always points to the same mutating instance. When we read out the value, we get the live value of the class object. Out of the box, we cannot save a snapshot in time of a mutable object. Our first workaround. Some classes, but not many, have a clone operation that effectively creates a new class with a copy of the same state. If we tell it to clone and save the new cloned object in a pad, then, assuming we don't do anything to update this clone, it should remain an unchanged copy of the original class at the point in time it was cloned. Problems with this approach is that most classes do not have a clone operation. Only exists for a handful of classes. One of the consequences of this snapshot behavior is that the undo node that comes with V4 Gamma will work out of the box on records. If your application data can be encapsulated in a single record, then you only need one node to implement undo for your whole application. If I make a few pushes to this undo node and then press undo, you'll see that working as expected. On the right side, it doesn't work. As we discussed before, it's only able to save the latest reference, and when we hit undo, unfortunately, it doesn't work. One workaround is to create a mutable and immutable version of your object. Then you need operations to convert to and from this immutable version to the runtime class version as required. This is verbose and requires maintaining 2 copies of your object, which might be unappealing. However, in the scope of your whole project, it might not be that much work. If undo is something you add at the end of your project, then it's not such a big deal to make that one immutable copy of your main runtime class then. Another workaround is we can use serialization to make a static copy of the class automatically. This is quite an expensive approach, but on a modern machine, there could be plenty of use cases where this performance is totally fine. For example, keeping a memory of the state of pieces of a chessboard, where you're not going to update it that frequently, it's not that much memory, it might perform fine, although it's a bit of a hack. Can you believe we are already at part 5 of this deep dive on mutability? Doesn't time fly when you're having fun? Thanks for all your patience and focus so far. This section looks at how classes can make the order of operations unclear. Let's jump into the examples. On the left is our record. We have some operations that lead to our result at the bottom. It's pretty straightforward to read this data flow and see how we achieve our result. We set byte A to 250, add 2 to it, and then divide by 2. It gives us 126. Or if we reorder these blocks, then we set A to 250, divide it by 2, then add 2 to it, giving us a result of 127. That's pretty straightforward. On the right side, let's do the same operations with classes. And for the purposes of illustration, let's do it as parallel operations, just because we can. You see the result is 126, which means that the order after set byte A is to increase by 2 and then divide by 2. Enabling the blocks in a different order does not change that. The issue here is that there's nothing about the coding that's telling it what order to perform these in, and it's an order that might change in different compilation scenario. The first workaround is the most obvious, verticality. For both records and classes, patching in series removes ambiguity about the order of operations. If we rearrange the class order, we get the expected result. Also note the absence of the yellow mutable warnings because there is no possibility of ambiguity here. There is another way to specify order when you have classes operating as a process node. If I open the top left menu here, sorry it's so small, inside the process node submenu, I can swap the order of the operations add and divide. Create will always be the first operation, but any operations under that, I can change the order they're executed when the process node is run. There is one more solution that could come in handy for specifying the order of operations of a class. A do region forces order of operations by resolving code inside the region before anything connected to the outputs of the region. And in fact, that's all it does. In this case on the left, you can see that if I put the tooltip over this chain of nodes building up a path, there's the path being built up. Now, if I want to extract those same images for use in the program, even when I use the clone node, I'm still only getting the final result. That's because the class that's passed to the input of these clone nodes is already the final result. To solve this, on the right, I can use the do regions to force it to clone the path at a certain stage of drawing. I couldn't achieve this with just vertical stacking because the clone SK path only has one output, which is the new cloned class. Welcome to part 6, where we take the mutability concept to collections. Specifically, we will cover what is the difference between spread and SpreadBuilder. First, what's a collection? A collection is a type for organizing data. In .NET, there are many types of collection. Examples are array, sequence, dictionary, and in V4, spread. If you check the node browser for type collections, you'll see lots of them. All the simple collection types are immutable. Most of them have mutable versions, and you can tell because they either have mutable or builder in the name. So, just like single objects, collections themselves can be mutable or immutable, and they mostly have the same pros and cons. A collection can be simplified as a table in memory that points to other objects. If you update an immutable collection, you make a new snapshot of that table. If you update a mutable collection, you edit that table in memory directly. One thing to clarify quickly, Does the mutability of a collection affect the mutability of objects inside? The answer is no. You can have an immutable spread of mutable classes or a mutable spread builder of immutable records. It's a bit oversimplified, but the collection is just the table pointing to the objects. The table can be changed or copied without changing the objects themselves. Why should you use immutable collections as standard? I think the best reason is because order of operations is always clear with immutable types. For example, if you have several operations that insert slices in a spread, it would be a nightmare if you couldn't guarantee the order that these happened. Remember back in the first part, we said immutable types didn't generally have a performance issue? Well, now we come to the exception. When an immutable collection is quickly updated, then this is a case where immutable collections can have a performance impact. An example would be a loop where you add 1,000 items to a spread. Why is this an issue? Because making a new immutable copy of an object when that object is a table means that table gets bigger every iteration, and you spend a lot of time copying parts of the table that haven't changed. With our example above, the table just gets one row added, but the whole table is still copied each time. The solution is to use builder mutable collection types. A mutable collection means each add operation can just add a row to the object that's already there. Builder types also have a special operation toImmutable to convert it to a regular immutable collection type after it's been built up. Let's see this in action with a little test. All these tests do the same thing, which is make a grid of coordinates. Let's look inside the first one. They all do this with a nested for each loop. It says for the first x coordinates, make a vector 2 with every other coordinate on the list to make a column of y coordinates. Then it does the same thing for the next and the next and the next x coordinate, so in the end we achieve a 75 by 75 grid. In this case, this should be the worst performing of these. Let me just go back. The one we just looked at should be the worst performing because it uses a simple add spread node to build up this immutable spread of coordinates. Let's enable it now, and hopefully it doesn't crash my screen recorder. You can see the update operation is very slow there. Let's look at the second version. The difference with this one is it uses the built-in splices to collect output, and so we have a spread of spreads there, and then it uses a flatten node to reduce it to a single immutable spread. I would call this the naive solution using the splices and flatten. At least it is for me, and I'm quite naive. Technically, it's still all immutable spreads. However, under the hood, the splices, the flatten, and some other nodes like cons use mutable collections to speed up cases. So this should be faster than the first version. Let's go back and run it. And that's massively faster, and in fact, totally acceptable performance if you're doing this every single frame. All right, the third one should be the fastest. Let's have a look how this one works. This uses the add operation, but instead of add spread, like the first example, it's add spread builder. There are two other things to note here. One is that we have a specific spread builder stored in a pad, and we are clearing it and reusing it every frame. This means the object assignment code in the background does as little as possible. It's not even creating a new spread builder each frame, it's reusing one that already exists. The second thing is that we included a toSpread function at the bottom, as after you've built your spread with Builder, you want to return it to an immutable regular spread for further processing. Let's run it. Okay, and that's the fastest, but it's only a little faster than version 2. So what did we learn? Our first conclusion is always avoid add spread for any serious loop count. Always prefer the splices and nodes like cons, flatten, as these have optimizations. If you are still having performance issues, use SpreadBuilder for the very fastest results when building large spreads. Afterwards, use the toSpread node to convert to a normal immutable spread. But it's not such a dramatic difference using SpreadBuilder over using the normal splices. We are finally at the conclusion. Thanks so much for your patience. We have spent plenty of time swimming in the details, and hopefully this helps you make the right choice of mutable versus immutable for specific use cases. or helps you solve issues you've run into with these already. For the conclusion, we zoom out again to the architecture level when you're thinking about your next application. And if you're thinking, oh, should I use a record or a class because of something you've learnt today, I'd ask you to consider if that's really the right question. Instead, I'd encourage you to look into design patterns. If you haven't heard of these, they are larger approaches to solving common software development problems. Sometimes a pattern will already call for a mutable or immutable type. There are some links here to documentation and some examples of these that have already been implemented in V4. And this brings us finally to the end. Thanks for your patience on this long video. Hopefully I won't make them so long in future, but I wanted to ensure I covered this topic comprehensively. Check the description below to download the patches. If you have feedback or you think there's something I got wrong or could have explained better, let me know in the comments. My greatest hope is that some of this has been useful for you. Cheers.